In this web clip, we'll discuss the diffraction of waves. This picture shows a typical example of diffraction of water waves incident from the left on a small slit in a screen. And what you can see is that the wave doesn't go straight, but typically can bend around corner. And at certain distance from the slit, you see a diffraction pattern occur with a certain opening angle. And so what we'll discuss is the relation between the opening angle of the diffracted wave in relation to, on the one hand, the size of the slit, size d, and on the other hand, the wavelength of the wave. In this case, water waves, but in our case, typically light waves. And the relation between the two is approximately diffraction angle is lambda over d, an equation that I like to call the most important equation in optics. The origin of diffraction is best understood by using the concept of secondary sources introduced by Huygens. So, using secondary sources, you understand that the propagation of a wave incident on a slit, you can envision that propagation as being due to a lot of sources, secondary sources, on the wave front of the wave. Each of these secondary sources emit its own circular wave, and it's the interference between all these waves that result in the propagation behind the slit. And so what you then see are a couple of things. You see, for instance, that the wave can bend a little bit around corner. You see that nearby the slit, in these bended waves, there are certain interference patterns visible. And finally, in the central part, there's still the main wave visible. But if you go further and further away from the slit, you'll see that the interference pattern becomes visible in the full structure. And that actually the size of this structure scales inversely proportional to the size of the aperture. I already introduced this simple form of the equation of diffraction, which shows the relation between the opening angle of the diffracted wave in relation to the size of the aperture and the wavelength of the wave incident on the slit. This equation is only simple if you satisfy three criteria. First, you have to be far away from the slit. Second, the angles in the diffraction pattern have to be much smaller than 1. You have to be in the paraxial regime. And finally, this expression applies only to diffraction from a slit and not to diffraction from a circular hole, as we'll also consider during this lecture. So the first criterion for this simple expression to apply is that you have to be very far away from the slit, in the far field. With very far, I mean that the size of the diffraction pattern should be much bigger than the size of the aperture. And if that is the case, the further you go, the larger the pattern becomes, but you can most easily express the pattern as a function of angle. The second criteria is that the angles involved should be much smaller than 1. You have to be in the paraxial regime. If you're not in the paraxial regime, so if these angles become bigger, then the actual equation is not theta is lambda over d, but is sine theta is lambda over d. And with this angle theta, given by this expression, we mean the angle between the central maximum, so the straight through ray, and the first minimum in the diffraction pattern. The third and final criterion is that this expression, this general expression, applies only to diffraction behind a slit, so a two-dimensional configuration. If you consider diffraction behind a circular hole, so a three-dimensional configuration, then the equation looks somewhat the same, Sine theta is lambda over d, but it acquires an additional prefactor, 1.22. So let's look in more detail at each of these three criteria that you need for the simple expression of diffraction to apply. The first criterion is that you have to be in the far field, sufficiently far away from a slit, illuminated in this picture from the bottom. And here you go further and further away from the slit, and you notice the following things. If you're very nearby the slit, the diffraction pattern is still pretty weird. It resembles the step-like intensity pattern that you expect behind the slit, but it acquires a couple of fringes, which are called Fresnel fringes. And this regime nearby the slit is called the Fresnel regime. If you go further and further away from the slit, you notice you get less fringes, and at some point the pattern more or less stabilizes, in the sense that the shape of the pattern remains the same, but the further and further you go, the wider the pattern gets. You get a pattern where you have an intensity as a function of angle only. That's the far field that we'll consider most of the time during this lecture. And this far field regime is also called the Fraunhofer regime of diffraction. If you wonder where the transition is, in this picture is somewhat here, between the Fresnel regime and the Fraunhofer regime, the simple criteria is that the size of the diffraction pattern should be bigger than the size of the aperture. So if you consider this simple expression, diffraction angle is lambda over d, and if you're at a distance L behind the slit, then the size of the diffraction pattern, L times theta, is L times lambda over d. And for the Fraunhofer regime to apply, this should be bigger than d, much bigger than d, which means that the distance behind the slit should be bigger than d squared over L to be in the Fraunhofer or far field regime. This slide shows the mathematical difference between the Fresnel nearby and the Fraunhofer far away regime of diffraction. In both cases, the field at the detection point originates from the interference of a series of secondary Huygens sources within the slit. And the essential aspect of this interference, of course, is the phase difference between these sources, which is related to the wave vector times a path length difference between the various paths from the source to the detection point. In the Fresnel regime, you need the law of Pythagoras to calculate these path length differences, and situations are somewhat complicated because rays are emitted under different angles. In the Fraunhofer far field regime that we'll consider during most of these slides, situation is easier because if the detection point is very far away, the rays emitted by the secondary sources within the slit are all more or less parallel. And hence, the path length differences between these rays is related to their position in the slit, which we denote by y, and the angle at which the rays are emitted via this equation, which I'll show in more detail in the next slide. It's cute to see that this far field regime is also reached if you use a lens. Because if you use a lens, you can image a point at infinity to the focal plane of the lens. So hence, also, if you use a lens and look in the focal plane of the lens, you see a diffraction pattern which is the Fraunhofer diffraction pattern of the slit. So let's derive the diffraction pattern far behind the slit, a diffraction pattern of which the essential feature is summarized by this equation: sine theta is lambda over d, or lambda over a, where a is the size of the slit. So we consider the far field diffraction pattern, and we look at rays of light emitted by a series of Huygens sources within the slit. Rays of light emitted at an angle theta with respect to the surface normal. We label these point sources within the slit, these secondary sources, by their position y inside the slit, where the source in the top is at position a over 2. A is the diameter of the slit, and the point at the bottom is at position minus a over 2, at least if we define y is 0 as the center of the slit, which is the most convenient. You already see that if you consider this is a wavefront, if you look at the interference and call this the reference length of the central ray, then these rays are shorter and these rays are longer. And the path length difference between these rays you can find if you draw a small triangle and realize that this angle is also theta, as this angle is theta. And then you see that this path length difference, delta L, is minus y times sine theta. And I say minus here, not that relevant. It's related to definitions. It's because you have to go to negative y's, to positions below the center of the slit, to make the path length longer, if you call this a positive angle theta. So for the calculation you need the phase factors of these various contributions, and so what you need is you need to integrate all these contributions. You need to integrate I, K, delta L over the slit. So from position a over 2 to position minus a over 2 to position a over 2. And this factor, K times delta L, we just expressed as minus I K y sine theta dy. We can also express, or write it a little bit shorter, as ky times y dy, where ky is the y component of the wave vector, is k times sine theta, per definition you might say. So to summarize, we considered the diffraction pattern far away behind the slit, a pattern as a function of angle. We calculated by dividing the sources within the slit as a series of Huygens sources and adding all these Huygens sources. And the outcome we found was that the field far away as a function of angle, but instead of angle we used a rewrite in terms of the y component of the wave vector, k times the sine of theta. And then the field far away as a function of angle, or ky, depends on the field in the slit, integrated over the slit, and then multiplied by phase factors which are related to the phase differences between the various sources in relation to the phase of a central ray. And these phase difference we express in various ways, like k times delta L, or as minus ky times y. So This is the general form. It's a nice compact form, but I also wrote it down because it is a very general form that you will encounter also in the second year. It's called a Fourier relation. And so it relates the field in the slit to the field far away via this expression with the exponent. That's a Fourier relation. Now, if you go back to the specific case of a slit, you integrate y between minus a over 2 and a over 2. It's an integral of an exponent, and you know how to deal with integrals of exponents, hopefully, because if you have an integral of an exponent, you basically get an exponent divided by this thing, right? And so here in this expression, I already substituted a over 2, minus a over 2, and then I rewrote the outcome in this form, where you see that the field far away is proportional to the size of the slit, naturally, but also to this expression sine beta over 2 divided by beta over 2, where beta is the maximum phase difference between the light emitted from the top of the slit and from the bottom of the slit. So this beta is k times delta L max, which you can also rewrite as ky times a, or this expression. So how does this diffraction pattern sine beta over 2 divided by beta over 2 look like? You have to realize this is a field. So the intensity is, of course, the square of this field. And then if you plot it, you find this result. You find that the intensity far away behind the slit is maximum on axis. You can call that 100%. And then at some point, there is a dark fringe. Then it becomes brighter again. Second dark fringe, bright. Third dark fringe, or line. And this equation, sine theta is lambda over a, applies to the angular distance between the first minimum and the central maximum. And it's the same as the distance between the first and second central minima, etc. And if you wonder what the brightness intensity of the secondary fringes are, then it's given here. The first intensity maxima is at almost 5% of the central maximum. This slide gives a second look at the diffraction equation and is mainly meant to understand this phasor diagram in the book of Young and Friedman. I already mentioned that beta is the phase difference between light emitted from the top and the bottom of the slit. A phase difference which is related to the maximum path length difference via phi is k times delta x max. And this diagram shows the contributions of the various Huygens sources in terms of small arrows in the complex plane. The standard phasors of the form exponent I phi. And you see here as a reference, it's the light from the bottom of the slit. And if you go to other sources, you see that these phasors, they bend, they point in different directions. And you have to integrate all these phasors to find the total field from the slit. And if you have that picture in mind, you can understand that you get destructive interference of the light if the max phase difference, beta, is an integer of 2 pi. Because if beta is an integer of 2 pi, basically you have all these phasor contributions and they loop around and they end up at the bottom again. So at zero field at destructive interference. if you, as we did, use the central beam as the reference, then you might like to draw the phasors as a series of small errors, and then you get destructive interference if the contributions of all these phasors fill the unit circle. Again, beta is m times 2 pi. In the previous derivation, we considered diffraction behind a slit. Now let's briefly look at diffraction behind a circular aperture in a screen. The diffraction pattern behind a circular aperture will be also circular, rotational symmetric. And to calculate this diffraction pattern, we consider a slice through the pattern, and we consider only light emitted at an angle theta in the y direction. So we consider kx is 0 or theta x is 0. We consider only the y dependence. But later on, it's easy to rotationally get the other components. So what we have to do is we calculate the field far away, so as a function of theta x and theta y, and we get that by integrating, adding all the secondary sources within the now circular aperture. So we perform a two-dimensional integral, and each component has a factor e to the power a phasor exponent I phi. Now, if we consider kx is 0, only slices in the y direction, then the integral over x is relatively simple, because each x component has the same phase vector, and we only have to take this length into account, a length that we easily get by Pythagoras. So hence, this two-dimensional integration can be written into a one-dimensional integration, which still looks like a nasty beast, but it's an integral that occurs more often in physics, and hence people have defined a special function. Actually, a guy called Bessel has defined this first-order Bessel function. So the diffraction pattern behind a circular aperture is given by this ratio, not sine beta over 2 divided by beta over 2, but J1 beta over 2 divided by beta over 2. Now let's look at the shape of the diffraction pattern behind the circular aperture. A diffraction pattern which you can express as the field as a function of theta x and theta y, far away behind the aperture, but typically, of course, we talk about the intensity, so the field squared. And this intensity pattern, the diffraction pattern, is circular symmetric, as the whole is circular symmetric. So it doesn't matter whether you look in the theta x direction or in the theta y direction or in any other direction. The pattern is always the same. Most important, the shape of the pattern looks somewhat like the sine beta over 2 divided by beta over 2. There's a central maximum and a couple of rings, dark rings and bright rings. And if you look at the precise pattern, if you look at the angular distance between the central maximum and the first minimum, a distance that you typically say, this we call the diffraction angle, then you find an expression that looks a lot like the expression sine theta is lambda over d for the slit, but now there is a prefactor 1.22. Basically, because this minimum, the first minimum, is the first zero of this Bessel function, and that first zero doesn't occur at pi, 3.14, but at a slightly larger value that is 1.22 times larger. And if you want to understand why the diffraction pattern behind a circular hole is bigger than behind the slit, all you have to do is compare in your head the diffraction pattern behind the circular aperture with that of a rectangular aperture. And you'll notice of the same size, of the same diameter. And then you'll notice that the circular aperture is effectively somewhat smaller. And hence the diffraction pattern will effectively be somewhat larger because you miss sort of these sources. And that's where the factor 1.22 comes from. Finally, small detail. If you look at the intensity of the first maximum, this first bright ring, you'll notice that for a circular hole it's at approximately 3%, whereas for a slit it was at approximately 5%. Let's wrap it up and summarize the diffraction of light. We considered the diffraction of light behind slits and circular apertures, and we calculated diffraction by dividing the light source in terms of a series of Huygens sources and taking into account the interference between these sources by looking in particular at their path length differences, because each source had a contribution of the form of a phasor, which you can rewrite in terms of a wave vector and a path length difference. We did most of our calculations, basically all our calculations, in the Fraunhofer regime far away. And in the Fraunhofer regime, the field as a function of angle was most conveniently expressed as a function of the y component of the k vector, which is related to the sine of theta in this form. And this is then the field in the slit, and this is the diffracted field. If you're close by, you will see intriguing additional interference fringes that we didn't go into detail. That most of the lecture was about diffraction behind a single slit. For that, we found a diffracted field of the form sine beta over 2 divided by beta over 2. And the first minimum in that diffraction field was at sine theta is lambda over d. Whereas if you took diffraction from a circular hole, you obtained a similar expression, but then with a factor 1.22 for a circular aperture. Thank you for your attention.